Hello. Hello. Hello.
Hi, Professor.
Hello, Chris. Thank you for the triple hello. Hello. Thank you for the hello. Hello. Hi, good afternoon. How are you? And there's Yavi. All right. Good afternoon, Matthew. Okay, I'm running. I'm already. You're ahead of me now. All right, let's do this. But hello, Yavi. Hello, Chris. Hello, Amanda. Good afternoon. How are you? Good afternoon, Michelle with a Q. Good afternoon, Freddie with an R. Good afternoon, Marilyn. Good afternoon, Matthew. Good afternoon, Yavi. Even though that's a double because of the chat. Okay. Good afternoon, Melita. Good afternoon, Michelle with an F. Right. And here comes other. All right. And there's Amanda. All right. Now we're talking and listening. And there's Cheska. All right. Now this party is started. Okay. And I said hello to Michelle. Okay. Excellent. Excellent. Let's get going here. Hello. Okay. Okay. We are going to start a new topic today. We're in that period of the semester where it's cascading out. Well, happy holidays, everybody, I guess. I don't even know which holidays I mean, but quick summary of this is important. Like where we concluded last time, is this and it will come up again in various ways in our life by the end of this course, and also it'll come up. Well, anyway, here's the summary of what we found last Wednesday is that if you have a plane, oh wait, you can hear me, right? Hold on, just yeah, that's a yes, Jessica, or yes, okay, yeah, okay, thank you. All right. More people. Okay. Oh yes, you can. Okay, thank you. Awesome. And Jessica and Chris. Okay. And telepathically Yavi. Okay. So what we found last time is if you have a plane inclined from the horizontal, from the horizon at angle theta, and if it's a smooth plane, like not worrying about friction, we found that the acceleration along the plane due to gravity is g times sine of the angle. A equals g sine theta, and that points down the plane, like as per this diagram, right? That in this situation, as you're looking at this diagram, the acceleration of an object on that smooth inclined plane would point down the plane. And let me reinforce, by the way, I don't care whether that object is moving up or moving down. In fact, maybe it doesn't matter whether it's moving up or moving down. Either way, the acceleration points down, and the acceleration is some percentage of free fall acceleration. That percentage is determined by the sine of the angle, right? That's what we determined last time. And the big point, the big takeaway at the end of last class is that we find this to be true. We would find this result whether we choose a traditional coordinate system for which the x-axis is along the horizontal and the y-axis is along the vertical, or if we rotate our coordinate system so that the x-axis is parallel with the inclined plane. Either way, we get the same result. Okay, so and please take some kind of notes on this. Even if you want to write down more than just what's written here, please. It will come up again. And feel free to submit those notes for more points, in the note portal if that helps you. But the idea number one is whichever reference frame we choose, whichever coordinate system we choose, the laws of physics will be the same. The physics result will be the same. That's Galileo, right? That's a big principle of physics. But the operational, like what that has to do with problem solving, is that you get the same answer no matter which perspective you look at it from. But one perspective is a lot more mathematically straightforward, is a lot less mathematical computation than the other perspective. It has fewer sines and cosines. It has less algebra. Just that. It has a lot less algebra. It has a lot less fewer algebraic insights or leaps that you have to make, like solving the simultaneous equations is not nearly as difficult. It's not nearly as long. You have half as many sines and cosines. And you don't have to know things like sine squared plus of theta plus cosine squared of theta equals 1. My point is this, and this is a big point. Remember, in the beginning of this course, we sort of had two threads going. We have like solving computational quantitative problems that come from homework and come from velocity, acceleration, force, whatever. And then we have this other thread, which seems very conceptual. So we have these math looking like problems in physics. And a common theme that goes on with those problems is that people tend to kind of know what they're doing once they're started off. And once it's set up, the algebra or even the calculus doesn't tend to be as challenging or as upsetting as sometimes people think it's going to be in physics. But the challenging part tends to be, how do we set up these problems? How do we start them? How do we know what math to use, or how do we know what equations, et cetera, right? So that's one thread in physics in general, is these quantitative problem solving processes. But then the other thread in physics is this conceptual thing, like train of thought, which turned into Galileo's principle of relativity, planet Earth, all motions are relative, GPR form number 4, where I said VAC equals VAB plus VBC. And that's all very conceptual, right? And very, very like correctly. While we were doing those concepts, people tended to ask me, like in the chat or, in emails or whatever, like, wait, I sort of get this, but I sort of don't. And I don't really understand what any of this has to do with problem solving. Like, I don't see how to do this concretely. And quite right. Like, so there was a concrete problem solving thread in this class where the challenge is, how do you set up the solutions to the problems? And then there's this conceptual thread to the class that all ultimately has to do with Galileo's principle of relativity. And at first, it doesn't seem like they necessarily have anything to do with each other. But the real point is that Galileo's principle of relativity is the physics idea that tells us, once we get used to it, once we practice with it, it tells us how to set up the math that we have to do to solve physics problems. And specifically, here is a classic example where the way we get the acceleration down the inclined plane, the way it was done in lab, even before you really knew what was going on, or even perhaps it was even done by the instructor, like to get the acceleration down an inclined plane, the simplest, what we tend to do is make this seemingly surprising choice at first. We rotate the graph paper of our mind, we make the x-axis line up with the inclined plane, and then we take the force of gravity, which is vertical, and we say we've got to break that up into two components, mg sine theta and mg cosine theta. I'm trying to reinforce right now that the thing we do to solve inclined planes at first seems physically very unnatural. It seems like a weird physics thing to do that people like just memorize or whatever. It doesn't seem like something that seems natural. But what I tried to show you last Wednesday is that if you don't make this physical intuition of using Galileo's principle to rotate your coordinate system, then the math is really thorny. It's really long and tricky. And by math, I mean the algebra and the trigonometry. So what we do in physics is we make physical choices in order to reduce or simplify the mathematical computation. And the way we make those choices is 9 times out of 10 by deploying Galileo's principle of relativity or some version of it. Okay, and this is a classic, because what I showed, I'm going to move on in a second, but I'm just trying to summarize, okay, because it's going to come up again. I mean, this specifically will, and other versions of this will. I'm trying to say that the thing that seemed physically unnatural or strange, to rotate the coordinate system and to break up gravity into mg sine, mg cosine, we We were allowed to do it because of Galileo's principle, and we wanted to do it because if we don't, if you do the natural thing of just leaving the x-axis horizontal and leaving the y-axis vertical, and then just breaking up the vectors that look like they should be broken up, like the diagonal vectors, what ends up happening is you have a lot more math to do. And we did that math on Wednesday. And when I say we did a lot more math on Wednesday to get the same answer, please recognize that example that I did on Wednesday was not even including friction. All of what I'm saying now could totally apply to friction, like as in the lab. All of what I'm saying now could apply to friction, and you are responsible for friction, like as a physics person. But if you add friction into the situation and you don't rotate your coordinate system, then you have that many more, then you have one more force to break up. If you don't rotate your, like friction would also be broken up. So you would have one more pair of sine and cosines going into your algebra, and it's really a mess. I mean, it's solvable. It is solvable, but it's really a mess. So what's the takeaway? Two takeaways. One is, yes, on an inclined plane, the acceleration down the plane, the contribution made by gravity to the acceleration down an inclined plane is g times sine of theta. That is certainly one takeaway that you want to get comfortable with. And the other takeaway is, in general, when we have any kind of force acceleration problem, any kind of problem involving free body diagrams or F net equals ma in life in general, and this will include physics 204, when you have a force problem, you choose a coordinate system for, and please write this down. If you're writing nothing else down, like I'm going to move on in a minute, so please write this down. We choose a positive x-axis so that it lines up with the positive a direction. You line up your positive x-axis with the direction of expected acceleration. That is the strategy that hopefully Wednesday's class like demonstrated. If you don't do that, you're not wrong, but you have a lot more math work to do to get to the same answer. Okay, that's the takeaway. Again, line up, always choose to line up your x-axis with acceleration. That's the takeaway. Now I'm going to move on, like totally. You can stop me. I'm moving on because that's what I'm doing unless you stop me. You can ask questions about that. You can still ask questions about the lab. I think you already turned in your lab, but if you didn't, you can still ask me questions about your lab at any time. Next, so we're going to start a new topic now, kind of like basically our final topic for this semester. There's a homework that's been posted on this new topic. It's not due this Wednesday, it's due next Monday. It's a little bit long, but it's not that bad. Once we get into the ideas, we'll spend the next 2 days trying to help you do that homework that's due next Monday. If anywhere in the homework, if it makes a reference to a textbook, don't worry about it. I tried to cross that. Anything that it says to look up in a textbook, like I will explain to you, or you could look up anywhere on the web. Like this was long ago when we didn't have Khan Academy that was mentioned. Anyway, all right, so I'm going to move on. The new topic that the homework is about is work and energy conservation. Now I'm going to stop. I mean, I'm not going to stop. I'm going to start by telling you what work is. By definition, work is the path integral of force. Let me say that a different way. I'm going to say it many different ways. The work that is done, so this is a definition. I'm not explaining like why this is true yet or why this is useful or anything. I'm just telling you what something is. To do work in physics is to examine the force, the total amount of effect accumulated by a force acting on an object as the object is displaced from one position to another. I'm going to say that another way. I'm going to keep saying it different ways. Okay, so if you missed one, don't. I'm saying the work done to move, there's a definition, the work done to move an object, to displace an object from position X1 to a different position X2, the work done to displace an object from position X1 to position X2 is the integral from X1 to X2 of the force applied in order to move the object from X1 to X2. So it's the integral of force with respect to displacement. It's the integral of f dx, where f stands for force and dx stands for displacement, change in position, difference between two positions. Okay. Now I'm going to go another step further. The work. So here's this is just written down what I just said. The work done on an object or a particle or a system. I will use all those terms interchangeably. I'll tend to try to say on a system, but they all in effect mean the same thing. They mean on a thing. The work done on an object in order to displace the object from x1 to x2 is the path integral of force from x1 to x2. Now, what does path integral mean? Technically, it means integral with respect to displacement. In other words, it means integral for which the independent variable, the dx, the d whatever, actually means space. Like as opposed, where the dx actually means change in x and x actually means position in space, as opposed to point in time or point in temperature or something else like that. Okay, when the independent variable is actually space, and we integrate something with respect to that variable, it's called a path integral, like you're integrating along an actual spatial path. But technically it's a path, and you can write this down too. I'm going to be talking about this like all day today. Technically, it's a path. So I'm introducing a new term called a path integral. Path integral means an integral for which the independent variable is space, but it also technically requires, for something to be a path integral, means that the thing that you're integrating with respect to space is being multiplied by space by some technique known as a dot product. And I'm going to start explaining that today. Hang on. So what I mean is this. Okay. So technically a path integral is an integral of a dot product. Now, I have to teach dot product. I'm not assuming that you know what a dot product is. I'm going to start explaining that today. Also, I am assuming that you've taken some calculus courses as were required for this class. I am assuming that you have seen integrals and done work with integrals and are familiar with the symbol and the terminology and the techniques of integration. Am I actually assuming that you have mastered integration, that you are integral all right, fair enough. Okay, I was just about to address this. Okay, I'm seeing the chat. Hold on, the chat is lighting up. I've seen it. Right, okay, no. Here we go. It's happening. Here we go. Bring it, people, bring it. No. Yes, we're about to encounter an uptick in the calculus content of this class. That is absolutely what is about to happen right now. Now, this uptick is not a huge uptick. It's a bit of an uptick, and it's not coincidence that it's happening right now. As we get toward the end of the semester, we are starting to ramp up our need or our use of calculus in preparation for Physics 204, where calculus plays a very big and explicit role. Let me back up for a second. I mean, you could, whoa. Wait, yeah. Oh, do you guys have Professor Graph? Okay, look, I love integrals too. Actually, I don't even know if you're being sarcastic or not, but I didn't, and I think graph is only spelled with one F, by the way. But wait, is Cal is well, okay. Look, we of course we have to have a calculus moment here. And yeah. Oh, okay. Because Professor Emerson, he went to Cal. Oh, anyway, okay. So listen for a second. It's not at all a surprise to me or a coincidence that the minute I mention the calculus thing, all of a sudden, like, people go nutto in the chat. Like, yes, I understand. Let's back up for a second. and establish a couple of things. We all know that there was a calculus prerequisite for this class A. We also know that up until this point, we've mentioned a lot of stuff regarding derivatives for sure. And we tried to define certain important physics concepts in terms of their calculus counterparts, i.e. derivatives for sure. But you and I both know that even though you were forced to take calculus before you took this class, we also know that you didn't really have to do much with much calculus to this point in the class. For some people, that's a big relief. And for some people, that's like a frustrating disappointment that they had to take calculus to get in here. And then like they're saying, but where is the calculus? All of this is, now I don't know what your feelings are, but that's all true, that you had to take calculus to get into this class. And we keep making reference to calculus concepts, but we haven't really like forced ourselves to do much operationally with those calculus concepts. Yes, all true. Now I will tell you that it shifts pretty significantly in Physics 204, particularly if I'm your instructor, where we really do have to do calculus in Physics 204. And the whole thing is supposed to be kind of a gentle upswing. I will tell calculus is the language of physics, and I do love calculus. But let me get straight right now. Anything we do here, and also, yeah, we've been dealing with derivatives, which is one thing, and now we're about to deal with integrals, which is definitely a whole other thing. No matter who you are, it's one thing to sort of get okay with derivatives. It is another thing to sort of get feeling okay with integrals, no matter who you are. I mean, a lot of people are okay with integrals, but it generally takes more time to get there, and more like stretches of the brain and more practice. Anything we do here in this course for the next few weeks is meant to help us soften the blow when we get to Physics 204. That's number one. Number two, and I'm dead serious about this, I'm introducing this integral right here, right now, as a means of giving this speech that I'm giving right here, right now. This is not a digression. This always happens. What I'm here to say is, calculus is a big part of physics without a doubt. And yes, and that means really understanding the ideas of calculus and seeing them live in physics. So up until now, we've sort of just been like trying to insert the ideas. We're now going to move to the idea of integral, which is a harder idea. And we're going to start really using it, which is harder. I am not operating under the illusion that just because you took 2 courses in calculus that you feel okay with it. Anybody in the room who does feel okay with calculus, that's awesome, and that will make their life better, easier at first perhaps, but I'm not assuming, I am not, after 30 years of experience doing this, assuming that most of you in your private Idaho actually feel comfortable with calculus. I am not. I'm certainly not assuming you like it, and I'm not assuming that you feel that you're great at it, whether you might be or not. Also, I'm not assuming that those of you who are in the room who can solve a lot of calculus problems or get a lot of integrals correct on exams in math class and maybe even got an A, I'm also not assuming that just because you can do that, that means you understand what you're doing conceptually. Or just because you can solve an integral problem doesn't necessarily mean that you know when you're supposed to introduce an integral or why or what the heck it has to do with anything. I'm not assuming any of that. In fact, I'm assuming the reverse. I'm assuming. So I'm going to start talking about calculus, and I'm going to start building up some physics ideas through integrals rather than derivatives. And if that's a little bit jostling to some of you in the room, that won't surprise me either. I'm not here to teach physics with a background assumption that you're totally equipped with the calculus tool. I'm here to show you an application of calculus that actually might make you get more comfortable with the calculus as you go. Okay, for some of you, I will now start explaining physics concepts, and for some of you, you'll understand the physics concepts better because I make reference to calculus tools that you do understand. That's fine. For some of you, by explaining these physics concepts, hopefully you'll start actually seeing what the calculus meant in the first place. And if you ideally keep going back and forth and looking at the calculus with regard to the physics and then the physics with regard to calculus, you'll ramp up your understanding and comfort and command of both of them. So don't run away mentally just because calculus is about to come down the road. Like, face it. I mean, literally, we're here to get a new perspective on calculus and maybe in some of our cases actually start learning it for the first time. I will tell you, for my money, it could be just as productive for a lot of people to have a physics requirement before taking calculus as it is to have a calculus requirement before taking physics. I can definitely tell you that I found calculus, in particular integrals, I found them totally intimidating and abstract and confusing and didn't understand them at all until I got a lot of practice with them in physics over time. So I learned the calculus from the physics, not the other way around. Just for what it's, now that's not everybody, but just for what it's worth, that is a possibility for many of you. Now, okay, now, so we're about to do, after I look at the chat, which I will look at the chat, but we're going to start breaking down the idea of work as an integral. But as far as I'm concerned, I'm about to teach, like, we're going to go in steps. So again, don't run away and don't worry about it. And the homework that's due Monday doesn't require the calculus so much. So don't be intimidated by that either. There was one last thing I was going to say. But yeah, we're going to break it down in steps and build up what the integral is doing in the context of work. Work is an integral, but it's also the case that the most vivid, straightforward, I think, example of an integral that exists is the physics work integral. So it's like so if I break down the work integral, for some of you that, yeah, you get my point. Now wait, let me look in the chat. Hold on a second. I'm gonna look in the chat. No, like, okay, someone's in the chat. Okay, that was 7 minutes ago, but there's at least one person in the chat, like, honestly saying, like, oh, I'm really bad. Like, I'm super bad at calculus. And I'm going to tell you right now, the person that's writing in the chat that they're super bad at calculus, like, I actually think they're a super good physics student. So, I mean, I also believe it's a person that knows him or herself or they self fairly well. So I believe that person who's saying that they're super bad at calculus. I'm here to tell you that does not worry me or surprise me. We're gonna get better at this together. Honestly. Now, but yes, we do want to get it at some point in physics 204 because there's a lot of integrals in physics 204. But okay. So just bear with me. Okay. But and as we're going, let me know. Like, this is definitely an opportunity where you should be putting feedback. You can put feedback in the chat like, I'm really bad at calculus, but better than that, or more than that, is once I start explaining it, tell me in the chat like where you lose me or whatever. It's not going to go too fast. Well, we'll see. But okay. All right. So I'm assuming you've seen an integral before. I'm assuming you're used to the idea that whenever you see an integral or a definite integral, there's usually like boundaries, limits on the integral, and there's like that symbol, the S-looking symbol, and there's always, I know you all know this, whenever there's an integral, there's like something times d something. It's always d something, right? And most of us have just like memorized that if I'm looking at an integral, it's got to have a d something. Most of us at this point don't even know why that's there. I'm going to get into all that. But you recognize this as an integral, I think. And then this integral, this particular type of integral, has something embedded in it called a dot product, which I'm not at all assuming that anybody has seen before. All these are my responsibilities to explain and unpack, like going forward right now. So let's start with this. When I say that work, when I say that the work done to displace an object from x1 to x2 is the continuous sum of scalar products between force and displacement from x1 and x2. So the first thing I'm saying, what I'm saying is an integral is a continuous sum of product. I'm going to break that down further, but that is what an integral is. It is a continuous sum of products. An integral is you take a product like F times, like force times displacement. You take a force times a displacement, you get the number for it, you put it in a bag, then you walk to the next displacement, you multiply force times displacement, you get a number for that, you put it in your bag, you walk to the next displacement, you multiply force times displacement, you put it in your bag, you add up all of the force, you add up all those products together, and that's what an integral is. It's an operation of adding up a bunch of products. That is what an integral is. And I'll get into what I mean by continuous like soon. But so in larger terms, the work that you do to move something from here all the way to there is the amount of force you had to apply to it to move it from here to there, plus to multiply together, plus the amount of force that you had to apply to it to move it from here to there, multiply together, plus the amount of force you have to apply to move it for, like, if you think of one big trip as a sum of lots and lots of little trips, for each one of those little trips, you multiply the force times the displacement, you get a number, a product for that multiplication. You add up all the products together. The total is what we mean by an integral, and the total amount of force times all the displacements is what we mean by work, okay? So that's what it is. That doesn't explain why that's what it is. That doesn't explain what we're doing with it yet. We'll get to all that. But first of all, that's what work is. Now I'm going to break that down further. Oh, okay. Well, yeah, a little background here. Like up until now, the biggest aspect of calculus that's been in this course has been the emphasis on derivatives. Just to remind you, like acceleration is instantaneous acceleration is defined to be the derivative of velocity with respect to time, right? And instantaneous velocity was defined to be the derivative of position with respect to time. Like that's what it says in the middle of the page here. A equals, is defined to be dv dt, and dv dt is defined to be dx dt. So A is d2x dt, the second derivative of position with respect to time. And like the big concept of this course is that acceleration is where the action is. If you're trying to predict where something is going to be when, you want to know it's acceleration, because velocity is just in the eye of the beholder, right? Like velocity, all velocities are relative. They are just a statement of who's looking at what. But acceleration is a bit more objective. Why? Because acceleration is always accompanied by net force, right? So so far to this point in the class, the sort of whole program of how we predict where something is going to be when, the whole program is we use, like as far as where we are right now, is we use these free body diagrams to analyze force, to analyze net force. We relate the net force to acceleration, and then once we get the acceleration, we use all of our original kinematic relations, kinematic equations, to infer position and time in the future, if that's what we're trying to predict, or position and time in the past, if we're trying to solve a crime, like literally. But think about that for a minute. What we've been doing up until now, every time we draw a free body diagram, such as the example from your lab, the one that like right in the middle of the page, we draw all these arrows coming out from a dot. The reason we're drawing all these arrows out from a dot is our focus, as it says, well, it says at the bottom, a free body diagram focuses on all the interactions affecting a point of mass in a point of space at a point in time, right? Like literally, we are asking, how hard is something being pushed or pulled in all these directions right now, right here? And our belief is if we add up all those forces that are acting right here, right now, we will get right here, right now, the instantaneous rate at which that point of mass is going to accelerate. And from that, right, so we know the net force right here, right now. We infer from that the acceleration right here, right now. And from that, we infer where it's going to be in 5 seconds, or how many seconds it'll take to be in 3 meters, or something like that, right? In other words, the whole program up until now was a derivative-based program, because derivatives are instantaneous rates of change, right? The derivative of some graph is the slope of the tangent line to the graph at a point. The whole idea of derivatives, whether you're thinking of it in a math class or in a physics class, the whole idea is that if you have this crucial information describing a point on a graph, or more physically, a frame of some larger motion, the whole idea is if we know the information describing the frame at the present point, then from that we can infer all of the future frames and all of the past frames of the larger movie. Like, that's the idea. Whether you're calling it derivatives in a math class or you're calling it instantaneous acceleration and forces and free body in a physics class, the idea is we are going to the limit as delta t approaches zero, right? We're focusing all of our attention on a pixel, on a dot, with the belief that by understanding exactly what's happening at that arbitrarily small interval of time, that infinitely small interval of time, we somehow know what's happening over the whole finite segment or continuum of time. I'm going to say one last way and I'm going to move on. We've been believing that if we have all the information appertaining to a point, we can infer what's going on for the whole curve. That's a derivative picture. That's the importance and the use of the derivative. Now we're going to shift and go in the other direction and say, wait a second, okay, that's fine. Like, that's not wrong. None of that is wrong. That's like super useful and super true. And it never goes away. I'm just like, okay, but we can look at things from another perspective. What we're now going to do is ask, instead of what's a force doing right here, right now at this frame, we're going to step back and say, what's the effect of a force acting throughout some continuous segment or region of space? So what work is in English, sort of English, work is the accumulated effect of a force acting throughout some region of space, not at just a point, but throughout some region of space. And that's, yeah, so that's what this says. Now we will ask, what is the effect of a force acting throughout a finite continuous region of space? That question that we're going to ask now, that invites the integral rather than the derivative. And let me say again, I'm not assuming you understand integral. I mean, I'm assuming you've seen integrals and worked with them. I'm not assuming you're totally comfortable with them, but I'm telling you right now, every time I say this, that what an integral shifts our focus from an integral is the effect of some dependent variable, some output. It's the effect of some function over a finite interval. It's derivatives look at points. Integrals look at regions. In fact, I think I'll say this quickly too. Remember at the beginning of the year, of the semester, like in the first week, I think I made a kind of a big stink about, like, sometimes in physics, you're looking at quantities at a point, and quantities at a point can be more precise but harder to picture. And other times you're looking at quantities as they apply to intervals or regions or separations between points, right? And those are often easier to picture, but harder to be exact about. Well, that's where we are now. We're going to use integrals to talk about forces acting throughout regions, through finite continuous regions. Okay, what the integral is, okay, I already said this once, but what the integral is a continuous sum of products throughout some finite continuous region. I keep using the word continuous, and I will keep using the word continuous. I'll be more detailed about it in a couple of minutes. But when I say continuous, what I mean is infinitely divisible. When I say continuous, I mean something that's not chopped up into countable sections, but something that's smooth, for what it's worth. And well, you'll see. But that's what I mean when I say that. So let's see what I'm talking about here. So I'm going to zoom down. I'm going to build up the need for the calculus from starting from a vantage point where the calculus isn't necessary yet, and we'll see how it becomes necessary. So here's what I'm going to say. Consider, that says consider. I don't know, that got erased. Okay, yeah. Okay. I'm going to say consider a small but finite displacement known as delta x. Okay, like you've used deltas a million times before. Delta always means difference. I mean, sometimes people say it means change. I think difference is a better word for it. Delta always means difference, but I'm going to, from now on, starting now, I'm going to be a little bit more careful. And I'm going to use delta whenever I mean small but finite difference between two values of a variable. So it says up in the blue, I know it's very hard to read up in the blue. I'm saying up in the blue that in general, if you have any variable, call it Z. I'm using Z as just any general variable at all. Delta Z from now on would mean a small but finite difference between two values of Z. Okay, I'm just saying that if I ever use delta from now on, I mean a small but finite difference between two values of a variable. So delta X means a difference between X2 and X1. In this case, in physics, X stands for position, right? I mean, it always has since the beginning of the semester. X is the position variable, right? So if we say delta X, we mean displacement. We mean small but finite difference between, we mean X2 minus X1. Okay. Then I'm going to say right now, if you have a small but finite difference between two positions, if you have a measurable difference between two positions, X1 and X2, we're going to define delta W. We're going to define a small amount of work to be force dotted with multiplied by small amount of displacement. Now notice again, I'm talking deltas. I don't have any D's anywhere in what I'm saying right now. I'm saying delta, and delta means small but finite. So if you have a small but finite amount of displacement, then the small but finite amount of work is defined as force times that small but finite amount of displacement. So let's take the simplest example possible. Let's just say we have some box of mass M, and you push it with some force F, and you push it through. Sorry. Wait. Sorry. Yes, Melita. Sorry. Do you want me to go back?
Yeah, sorry. Can you just explain the point that you had in blue and small?
Oh, sorry. Say it one more time. Say it one more time. Can I explain what?
Sorry, can you just explain the point that you had in small and blue?
Yeah. Okay, sorry. The thing I have in blue, it says exactly the same thing as I'm saying in black, only in blue, I made it a Z rather than an X, just because this is like, for purposes of later, I'm saying that actually from now, so whenever I use Z in the future, Z stands for like any variable at all, whether it's X or Y or temperature or something like. So what I'm trying to say up in the blue is just, let me back up for a second. What I'm saying here in black is that delta X means small but finite difference between two values of X. That's how we're going to use it here. Delta means small but finite difference between two values. But then up in blue, all I'm just trying to say is, oh, by the way, that notation we're going to use forever now. Like, it doesn't only just apply to X, like in space. Any variable that we'd ever have, if we put a delta before it, I want to emphasize that deltas mean small but finite differences between values. So like in math class, when you have slope equals delta y over delta x, and what you really mean by that is y2 minus y1 over x2 minus x1. That's what I'm saying. Like, yeah, notice you use that notation, that delta notation, because the delta notation always in general means if you can subtract one value of a variable from another, if you can actually measure the interval between two values of a variable, then that's when we use the delta. Oh, okay, great. All right, awesome. And I'm glad, I'm glad and please, everybody do what she's doing. Like, stop me with, no, I'm glad. All right, cool. I believe her that she believes me. And for those of you who are thinking like, yeah, like, duh, like what I'm really secretly trying to say right now is that's what delta means, as opposed to the D that comes up in integrals that people generally do tend to get confused by, or just ignore, or just believe. Like, I'm trying to build up what that D is all about. So I'm starting with what delta means. Delta means small but finite difference between two values of a variable. Okay, so to Melita and everybody else. Okay, wait, hold on. All right, okay, but I'm glad you did that. Okay, so wait, I'm here. Right, so I'm in the delta context now, where where some box is moved some small displacement call it delta X, and it's moved because someone came along with an F, with a force, like they pushed it or they pulled it throughout some displacement, right? So I'm saying, so this is the, and I'm also assuming that the force, so I'm assuming two things. I'm assuming the delta X is small but finite, and I'm assuming that the F in this case is like strictly parallel with the delta X, like the box moves horizontally and the push or the pull is strictly horizontal in the same direction. Like that's what I'm assuming in this example right now. So in this, so notice, everybody please notice, what I'm defining now is delta W. I'm defining a small amount of work in a small, simple case. It's not like the landing place, it's the takeoff point for this concept, okay? So delta W, a small amount of work, is defined to be, in this case, force times delta X, F times delta X, force times small but finite displacement. If you pushed, for example, if that box, if you pushed it with a constant horizontal force of 5 newtons and you succeeded in pushing it 3 meters, then we would say in that case, the work that you did on the box would be 5 newtons times 3 meters. And we're going to call that from now on 15 joules. We're going to say that 1 joule is 1 newton of force times 1 meter of displacement. Okay, so in that sense, it's somewhat straightforward. If all so that's what work is. It's like how hard you interact with something times how successful you are in displacing that thing. It's kind of like the effort you put in times the result that you got out. You could say that's what work is. So work is a product by definition. It's not division. You know, if either number goes up, the whole total goes up. But it's not addition. It's multiplication, meaning if either of the terms is 0, then the whole answer is 0. So if you don't push something, I don't care how far it moved, no one did any work on it. A hockey puck just gliding on frictionless ice is moving, but no work is being done. But also, if you push really hard against something like a wall, you could push really hard against a wall. The force could be really high, but if the wall's not moving, you're not doing any work on the wall. Okay, so in the simplest case, work is how hard you push or pull times how far the thing goes. And work is something just like force. You should put this in your notes too. Just like force is an interaction between two objects, so is work. One object does work on another. You can't like just have work or be work. You do work to something else. Push a kid down side, right, yeah, like totally. Now, actually, even with Chris's, I never totally know whether he's joking or not, but it's always like, because it's always like vaguely serious and vaguely entertaining. Yeah, like if you push a kid down a slide and see how far they go, that would be an example of calculating the work done that you did on the kid. One thing to be clear though about his example, you could calculate the work you're doing when you push a kid down a slide, as long as you continue to push the kid the whole time the kid is going down the slide. Like if you just push and then you let go, then you're not doing, like, then that's just an instantaneous force. So the whole idea of work is we're now talking about a continuously applied force, applied continuously throughout some space. And I'm not, again, to be clear, I'm not arguing. Oh, right. We definitely do. Yeah. Okay. And one day I'm going to know, on a scale from 1 to 10, how seriously should I take Chris? It's always a question. But I'm taking every one of these, but I'll definitely, yeah, like we should do a class field to the park, a field trip, but we're not going to. But yeah, as long as we're clear that work is the outcome or the accumulated effect of force being applied continuously throughout an interval of space, like, then I agree with Chris. But also now I'm just going to quibble for a second, just because here we go. Like, just know, we will get to a theory of this or something. We will make a claim about this at some point. But right now, this isn't even a theory, right? This is just like literally a definition. I'm just like, there's nothing to be wrong. I mean, and I know he's joking about the testing, but right. That's funny. Okay. Wait, let's go. Yes, let's go in both senses of the word. But just recognize, right now, this there's not even a element of true or false to anything I'm saying. It's just like literally triple equal signs. But okay, anyway, all right, you get it. You clearly get it. So now I'm going to go on. The case that I just gave, not even the slide case, but just the case of I push horizontally and the thing goes horizontally. That's the simplest possible case of work I could offer. They get more complicated from here, and they begin to require these slightly more advanced concepts of the integral and the dot product and all this, because in the case that I just gave, from which I'm going to build everything, in the case that I just gave, first of all, the displacement is small but finite. We have to address that. Like we assume the displacement was small but finite. But second, we assume that the force that was applied was strictly parallel. The force vector was in exactly the same direction as, oh, don't say Karen in the, okay, okay, yeah, we have to be, okay, that's funny, but we got to be careful. Okay. So the second thing is that we assumed in the case I just gave, when I just did 15 times 3 or 5 times 3 equals 15, two things made that simple. One, the displacement was small. You'll see what I mean in a second. And second of all, it was like a meters horizontal and force horizontal. There was no angle. So I have to one at a time deal with what happens if those assumptions are not that simple. So let's expand or relax these assumptions one at a time. First of all, what do I mean by small but finite? Like I keep saying that. I keep saying that delta x is what we use if the delta x is what we use if the displacement is small but finite. But what do I mean by small? How small is small? And here's what I mean by small. When I say, particularly when I say small but finite, I mean small enough to allow f to equal f naught. What? I mean small enough to prevent f, the force value, to prevent it from changing, from varying. So I'm saying, so that could be a couple of millimeters or it could be a couple of miles, depending on your context. But what small means is, I'm using delta x whenever the force that's being applied stays steady and constant. In other words, whenever we have one number for the f and we don't have any confusion about what number to use for the f, and we can just multiply that one number for f by the delta x, then things are comparatively straightforward and we don't need all the calculus or anything like that. If the delta x is small enough that f doesn't change, or put another way, if you have good reason to believe that the f is not increasing or decreasing throughout this interval of space, then, whoa, that was cool. Whoever just did that. Okay. If they do it too much, it probably won't be cool anymore, but that was cool. So that's the first thing. If f is a given number that doesn't change throughout the delta x, then actually that makes our life a lot easier. And truth told, that is true. So in other words, when work is done by a constant force, the integral issues don't arise. And the truth is, I think that's true for 99%, if not all, of the homework that's due Monday, because I believe the homework is called work done by a constant force. Okay, so that's one thing. Now, I still have to get back and deal with what do we do when f is not constant, when delta x is not small. I do have to get to that. But before I get to that, oh yeah, all right. So this is just an expansion of what I just said. Like, so just to be clear, if f equals f naught, if f is a constant, then there's no need to add up a bunch of products. It's one product, f times all of delta x. And so as long as f is not a function of x, as long as f does not vary, as long as capital F, force, does not vary as a function of little x displacement, or put another way, if you were to make a graph, and this will come up a lot right at the beginning of Physics 204 next semester, if you were to make a graph of force as the dependent variable and x as the independent variable, if the graph were horizontal, then there's no need for the calculus. Okay, so tuck that in your mind. but so we're going to maintain that assumption for a little while longer. Like, let's assume, for at least for the rest of today's class, for the next 20 minutes, let's assume we have a situation where you're pushing or pulling at a constant rate and something's being displaced. Then the amount you push or pull in newtons times the amount it's displaced in meters gives you the amount of work that you have done in joules. That's what we're saying so far. It is that simple. And you may already knew this from 7th grade. I don't know. Okay, but now we have to go a step further. Let's go to assumption number 2, or condition number 2. What if the force exerted on, so I'm reading the black at the bottom of the page. What if the force exerted on an object is not parallel with the object's displacement? Examples. Many, I mean, most real world examples have this aspect to them, such as back to the original sled on the, it's always children with me. I don't know what, oh yeah, because I have them. Right. Like if you have a sled on horizontal ground and someone's pulling a string in order to displace the sled, right? It's totally plausible and common that the force being applied to the sled might be from the tension in a string, and that force might be at some angle as measured from the horizontal, but the actual displacement is purely horizontal. So there's an angle between the force and the displacement. Remember, force is a vector, it has direction. Displacement is a vector, it has direction. It's very, very plausible that those directions might not line up with each other. And then we have to think about that. Because arguably, when you pull a sled, arguably, if you could get down, if you could get down on your knees and actually, like if you had a certain amount of force to devote to the sled, if you had a certain amount of muscular strength and you were capable of exerting no more than 10 newtons, one might make the argument that you'd like to get down on your knees and devote all of that 10 newtons of force entirely to the horizontal direction, since that's what you're trying to accomplish. One might argue, and I think argue correctly, that whatever amount of 10 newtons that you're devoting to pulling up on the string is not doing anything to help you in your goal. Like, unless there's friction and it's reducing the friction or something, but that's like another issue, right? Or similarly, your lab, the inclined plane, you have an object that is displacing along an x-axis, but and it's displacing, it's like accelerating down the inclined plane due to the force of gravity, but the force of gravity is itself pulling straight down. So there's an angle there between the force vector and the displacement vector. So the question is, how do we deal in these cases? And there is something to deal with, because again, because remember, anytime a vector is off axis, a vector can be resolved into 2 components, like one along each coordinate axis. And presumably, like say in the top example, I think it's easier to see, presumably T can be in fact, let me make a new, if you zoom in on T, we can resolve T into 2 components, right? A T cosine theta and a T sine theta, opposite and adjacent, right? And presumably it's the T cosine theta component that's really pulling the sled along the horizontal ground, and the T sine theta component is doing something, but it's not doing work, I would conjecture. So what do we do with this? Okay, I'm just looking at the time. Okay, force is a vector. F, it has direction and magnitude. Displacement is a vector, delta x. It has direction and magnitude. From now on, whenever I write down a vector quantity, when vectors are relevant, when we're in a vector context, I'll put an arrow above the letter standing for the quantity, right? And the question arises, like I'm telling you, work is by definition a force vector multiplied by a displacement vector. Well, we've never multiplied vectors before. Like, how do you multiply vector? Or what happens when you multiply vectors? Good question. Or put it another way, how do you deal? Like, I know how to multiply numbers. You know how to multiply numbers. I know how to multiply numbers on a number line. But if vectors are like if vectors can go in different directions and one can be on a number line and one can be on a different number line, how do you deal with multiplying things that involve direction? Good question. Glad you asked. Well, it turns out, how do we do multiplication when vectors are involved? It turns out that when vectors are involved, there's actually 3 different ways to perform multiplication in any context where vectors are involved. I'm not going to explain all 3 of them in this class, but I'm going to lay out 2 of them, and I'm going to lay out the 3rd one in the next class. There's 3 different ways to do multiplication when vectors are involved. One of those ways is the way that we need to calculate work. Let me show you what I mean. So in general, let's say you've got 2 random vectors, vector A and vector B. So they're random, like they're of 2 different sizes and they're of 2 different directions. Let's assume that theta is the angle, the acute angle between the tails of the 2 vectors A and B. Like, let's assume that A and B are pointing in different directions by an amount, theta. Notation-wise, I'm going to say from now on, if we're in a context where vectors are being used, then strictly speaking, we should include an arrow over any letter that designates a vector quantity. But if we're in a context with vectors and you ever see a letter without the arrow, that's not supposed to be a typo. That's supposed to refer just to the magnitude of the particular vector. In other words, we have given here vector A written with an arrow over it. A written with an arrow over it means the magnitude of A combined with the direction of A. But if I ever just write down the letter A, what it means by definition is the magnitude of vector A. Okay, the so to speak double absolute value of vector A. So that's just notation. I'm just trying to, you probably already maybe took it for granted, but I'm just trying to be explicit about that. That vector A with an arrow means direction and magnitude of A. A written by itself means just the pure magnitude of A, okay? And so let's say we've got these 2 vectors A and B, and let's say C is just some random number, or it's like this magnitude of some other vector whose direction I don't care about, right? Then, way number 1 that you could do multiplication involving vectors is you could take a vector and you can multiply it by a scalar. Like I could take vector A and I can multiply it by the scalar number C, okay? And if I do that, this may be obvious, but I'm just laying out the 3 ways of doing multiplication when you have vectors. If you have a vector, you can multiply it by a scalar. And that's like always legal. You can always do that. And if you multiply a vector by a scalar, what you always get is a new vector. Let me say that again. If you multiply a vector by a scalar, what you always get is a vector. And the reason for that, it actually makes sense. If a vector is an arrow with size and orientation, then multiplying an arrow by a certain number just enlarges or shrinks the arrow. You still have an arrow, but you have an arrow of a different size. In fact, that's why we call pure numbers scalars, because when you take a vector, an arrow, and you multiply it by a pure number, all you do is you scale up or you scale down the arrow by a certain factor, right? So if you're going 3 miles at 45 degrees to the northeast and you multiply that by the number 2, then you've gone 6 miles in the direction of, oh my God. Wait, sorry, is that me raising my hand because I just gesticulated? Sorry, is someone raising their hand or is that me? I think that is why.
You raised your hand.
So then it raised my hand. That's crazy. This is like artificial. Okay, the robots are coming. All right. I think we're putting Chris in charge of the class when the robots get me. All right, anyway, oh my God, I should not be freaked out by that, but I am. Sorry, I just recollect myself. It saw me raise my hand, so it raised my hand. Okay, anyway, all right, anyway. Grow up, yeah, grow up. Okay. Okay, so a scalar is called a scalar because it literally just scales up or down the size of a vector. Bottom line, when you take a vector and you multiply it by a scalar, you always get a vector. But that's context. That's like a thing that is true. But what if you have two vectors and you need to multiply? And that's the case here in this context of work. We have a vector called force. We have a vector called displacement. We want to multiply them. What happens? What do we do? Turns out there's two different ways. There's two more ways that multiplication can occur. You can multiply two vectors in a manner that produces a scalar, or you can multiply two vectors in a manner that produces a vector. Let me say that that's two important and that's a choice. That's two different tools of mathematics that we apply in physics. When you have two vectors, you can choose to multiply them in a manner that produces a scalar, like a pure number, a pure magnitude, or you can choose to multiply them in a manner that produces a vector. And now it's a choice. Any two vectors, you could do either one, just like any two numbers in life. You could decide to add, or you could decide to subtract, or you could decide to multiply, depending on like what you're trying to figure out, right? So there's two different forms there's two different ways to actually multiply a vector by a vector. Now, one is called a dot product, and one is called a cross product. The dot, I'm going to turn the page in a second, but just to give you the context, so since I know class is going to run out in 9 minutes. The dot product is the way of multiplying two vectors that produces a scalar. The cross product is, and some people call the dot product the scalar product of two vectors. The cross product is a way of multiplying two vectors that produces a vector. Some people call that the vector product or vector multiplication, okay? Those are two different choices. Again, it's just two different tools, two different operations. In physics, we ultimately absolutely need both of them. Right now, the one that we need is the one that multiplies two vectors together in order to produce a scalar. That's what work is. Work, and this again is just by definition. I'm not even trying to justify like why we care or what we do with it yet. I certainly will. But right now, I'm trying to say that a little bit of work is a force vector dotted with a little bit of displacement. That work is the scalar pure number result that arises when we multiply a little bit of force with a little bit of displacement in a certain way. I'm going to say one more. In other words, in the other example, when I multiplied 5 newtons by 3 meters and got 15 joules, I got literally 15 joules of work. We say that 15 joules of work was done on that block. We don't say 15 joules of work was done to the northeast or the southwest or anything. Work is not a vector, is what I'm asserting. It's just a quantity. So we use to multiply the 5 by the 3 or whatever, we use something called a dot product. How does the dot product work? The dot, so here's a definition now. This is a math thing. Assume that we have these two vectors, A and B, and they're separated by an angle theta. Then by definition for all time, the dot product of vector A with vector B is defined to be the magnitude of A times the magnitude of B times the cosine of the angle between them. I'm just looking at the time. Yeah, not specifically the cosine, like not the sine. Okay, and if you're trying to track this or trying to get a context, when we finally do the cross product, it turns out that has something to do with A, B times the sine of the angle between them. But we don't need to deal with that just yet. So specifically, the definition of work here, or a little bit of work, a small but finite amount of work, is defined to be a force vector dotted with a small but finite amount of displacement. Dotted means we take the magnitude of the force, multiply by the magnitude of the displacement, and multiply by the cosine of the angle between them. Why cosine? Well, if you were Okay. Cosine of any angle always spits out a value between 0 and 1, a fraction, a decimal, a percentage, really. When the cosine of 0 is 1, when the angle between two vectors is nothing, when two vectors are strictly parallel with each other, the cosine returns a full-bodied 1. So in the limiting case, in the simple example of what we did before, where the x is purely horizontal and the f is purely horizontal, right? All of the force is being devoted to displacement. Then we took the magnitude of that force, 5, we multiplied it by the magnitude of displacement, 3, and then without realizing it, we then took the cosine of the angle between them, but the angle was 0 and the cosine is 1. So we did, in effect, 100. So we did 1 times 5 times 3. So in effect, we did 100% of 5 times 3, because we're saying 100% of that 5 was fully devoted to the displacement of that 3, right? But the bigger the angle that there might have been between f and x, like if we started pulling up on an angle like the child with the tension in the string in the sled, if we start pulling or pushing at some angle, as the angle between the displacement and the force gets bigger and bigger, the cosine gets smaller and smaller. It goes from 1 down to 0, right? So when we if we multiply f times delta x times the cosine of the angle between them, in a way, what we're really just, since multiplication is commutative, what we're really just saying is, don't multiply the entire, at the end of the day, don't multiply the whole force by the whole displacement, only multiply a fraction of the force times the displacement. What fraction of the force? The fraction of the force that's devoted to the axis of that displacement. Like, what we're really doing in effect is just multiplication is commutative. So to say f times delta x times cosine theta is the same thing as saying f cosine theta times delta x. Like, we're not multiplying delta x by all of f, we're just multiplying it by the horizontal component of f. If f is really close to horizontal, that's going to be a really huge component, a really big percentage. But as the angle gets bigger and bigger and bigger, and f drifts farther and farther away from the axis of x, then the cosine will get smaller and smaller and smaller. The component of f that gets multiplied by x will get smaller and smaller. So in the limiting case, if you ask, in this case, if you're pulling and this is the last thing I'm going to say, I see it's 419. If you're pulling a sled along the ground, so the sled is displacing horizontally. The whole time you're doing that, gravity is also a force involved in the problem. Gravity is always there, pulling down, but it's pulling purely down while the sled goes purely horizontally. So even though gravity is a huge force, mg, and the displacement might be huge at delta x, the work done by gravity would be mg times delta x times cosine of the angle between them, and the angle between them is 90 degrees. Between gravity and some horizontal motion is 90 degrees, so the cosine would be 0. So at the end of the day, we would say, oh, gravity might be a force acting on the sled, but it ain't doing no work. The sled is moving to the right or left for reasons that have nothing to do with the downward pull of gravity. So at the end of the day, when I'm saying I know it's 420, what I'm saying so far is, in the case of a constant force, before we get to the calculus, first thing we should realize is that, so in the case of a small amount of displacement, small enough that the force is constant, a little bit of work is force vector dotted with displacement vector. F dot delta x means ultimately magnitude of f times magnitude of delta x times the cosine of the angle between them. That's the definition of work in the small case. That's where we'll end for right now. I'm still here if anybody wants to ask me any questions or move the pages back or anything like that. But the homework that's now due is due Monday. So we'll talk more about this Wednesday. Have a great 2 days. Welcome back. Quark bless America. I'm stopping the recording, but I'm staying here. Yes, have a great day.